Removable and jump discontinuities. In our previous class, we learnt about continuous functions. If a function is not continuous, then we call it as a discontinuous function. So, every function may be discontinuous at some point, not in all the points, not in all the points of the graph, but in few points those functions are discontinuous. In discontinuity, here these are the types, the removable discontinuity and the jump discontinuity. First, let us define what is removable discontinuity. Even though the original function f of x fails to be continuous at x is equal to x naught. Yes, the function may be continuous in all the other points except x is equal to x naught. It fails to be continuous at x is equal to x naught. So, in this point, in this particular point, it is not continuous. The redefined function becomes continuous at x naught. So, the function f of x is not continuous, that is fails to be continuous at x naught. So, we can redefine the function so that it become continuous at x naught. Okay. We have to redefine that function that fails to be continuous. Okay. That is, we could remove the discontinuity by redefining the function. Yes, from the function we are going to remove the discontinuity. At some point we are going to remove, at some point that function is not continuous. That function is discontinuous at some point. So, we have to remove that function by redefining the function. Such discontinuous points are called removable discontinuities. So, we can remove the discontinuities and those points, those discontinuous points are called removable discontinuous. A function f defined on an interval I belongs to R, which is a subset of the real number line, is said to have removable discontinuity at x naught if there is a function h from I to R such that h of x is equal to f of x if x is not equal to x naught. Limit x tends to x naught f of x if x is equal to x naught. Okay, so we are redefining the function. We are altering the function f of x and we are defining another function h of x that is continuous. Okay. Now, jump discontinuity. What is jump discontinuity? F be a function defined on an interval I, which is a subset of R, then f is said to have jump discontinuity at a point x naught belongs to I if f is defined at x naught. Limit x tends to x naught minus f of x. What is x tends to x naught minus? That is the left hand limit. And limit x tends to x naught plus f of x exists. What is limit x tends to x naught plus? It is right hand limit. Both are exist, but limit x tends to x naught minus f of x is not equal to limit x tends to x naught plus f of x. So, here in jump discontinuity, the left hand side limit and the right hand side limit are not equal. But in removable discontinuity, we can find the left hand side limit and right hand side limit and they are equal. Only in jump discontinuity, the left hand side limit and right hand side limit is not equal. Okay, but here it is equal in removable discontinuity. Let us see a problem. If f and g are continuous functions with f of 3 is equal to 5 and 2 f of x minus g of x is equal to 4, find g of 3. Here we have two continuous functions f and g and f of 3 is equal to 5 and another condition is given, that is 2 f of x minus g of x is equal to 4. We have to find g of 3. Okay, let's see the solution. F and g are continuous functions. Yes, they are continuous function. So, limit x tends to 3 f of x will become f of 3. Because instead of x, if you substitute 3, it will become f of 3. Similarly, limit x tends to 3, g of x is equal to g of 3. What is given? F of 3 is equal to 5. So, f of 3 is equal to 5 and 2 f of x minus g of x is equal to 4. So, for this limit, so limit x tends to 3, 2 f of x minus g of x is equal to 3. So, this limit is common for both this and this functions. So, limit x tends to 3, 2 f of x minus limit x tends to 3 g of x. 2 is a constant, so we can take it out. So, 2 into limit x tends to 3 f of x minus limit x tends to 3 g of x is equal to 4. So, instead of, okay, now we can apply the limit, that is 2 into limit x tends to 3 f of x. When you apply the limit x tends to 3, this f of x becomes f of 3. Here we can see that. Okay. So, 2 into f of 3 minus g of 3 is equal to 4. What is f of 3? It is given that f of 3 is 5. So, 2 into 5 minus g of 3 is equal to 4. So, to find g of 3, we can bring it to the other side and 4 to this side. 2 5s are 10, 10 minus 4 is equal to g of 3 and hence g of 3 is equal to 6. Here both the functions are continuous. Which of the following functions f has a removable discontinuity at x is equal to x naught? If the discontinuity is removable, find a function g that agrees with f for x is not equal to x naught and it is continuous on R. So, here we have the function f which has a removable discontinuity. At this point x is equal to x naught. So, we have to find a function. We have to redefine a function g that agrees with f for x is not equal to x naught and it should be continuous on R. What is the given problem? F of x is equal to x square minus 2x minus 8 divided by x plus 2 where x naught is equal to minus 2. If you substitute this value directly here, the denominator will become 0. So, it should not be continuous. We couldn't substitute that also. So, f of x is not defined at x is equal to minus 2. So, it is an indeterminate value. So, it is not defined at x is equal to minus 2. At this point, the function is not defined. So, limit x tends to minus 2, x square minus 2x minus 8 divided by x plus 2. Let us factorize the numerator. Okay. So, it will become x plus 2 into x minus 4. You can factorize at your own method. Okay, Amma. Limit x tends to 2, x plus 2 into x minus 4 divided by x plus 2. We can simplify, cancel x plus 2 and x plus 2 and here we get limit x tends to minus 2, x minus 4. So, now I can substitute minus 2. I can apply the limit now. So, it is minus 2 minus 4 and that is minus 6. So, the limit value exists. The value of this limit is minus 6. Now, we have to redefine the function. So, when x is not equal to minus 2, this function f of x exists the same. When x is equal to minus 2, the value of the function is minus 6. Here we have calculated it, right? When x is equal to minus 2, it is minus 6. So, we are redefining the function g of x as when x is equal to minus 2, it is minus 6. For all the other values either other than x minus 2, x is equal to minus 2, this function remains the same. Therefore, f of x has a removable discontinuity at x is equal to minus 2, but now here we have a function g of x and it is continuous. Let us see another problem of this type. F of x is equal to 3 minus root x divided by 9 minus x, where x naught is equal to 9. Here x naught, the function f of x is not continuous at this point, x naught is equal to 9. So, we have to redefine this function f of x. So, f of x is not defined at x is equal to 9. So, limit x tends to 9, f of x is equal to limit x tends to 9, 3 minus root x divided by 9 minus x. We can factorize the denominator. I write 9 minus x as 3 square minus root x the whole square. So, it is of the form a square minus b square. So, a plus b into a minus b. So, 3 minus root x divided by 3 plus root x into 3 minus root x. We can cancel 3 minus root x in the numerator and denominator. So, it is equal to limit x tends to 9, 1 divided by 3 plus root x. So, we can apply the limit now. 1 divided by 3 plus root 9. What is root 9? It is also 3. So, 1 divided by 3 plus 3. So, limit x tends to 9, f of x is equal to 1 by 6. Therefore, the limit of the function f of x exists at x is equal to 9. We have calculated. So, we can redefine the function now. The function f of x has removable discontinuity at x is equal to 9. So, we can redefine the function f of x as g of x is equal to 3 minus root x divided by 9 minus x if x is not equal to 9. When x is equal to 9, it is 1 by 6. We have calculated it, right? When x is equal to 9, it is 1 by 6. So, we can redefine the function like this. G of x is equal to 3 minus root x by 9 minus x if x is not equal to 9 and 1 by 6 if x is equal to 9. So, g of x is defined at all the points of R and it is continuous. Okay. Find the constant b that makes g continuous on minus infinity and infinity. G of x is equal to x square minus b square if x is less than 4. Bx plus 20 if x is greater than or equal to 4. It is given that g is continuous on R. So, g of x is continuous at x is equal to 4. Okay, it is continuous. And here the limit is 4. So, it is continuous at x is equal to 4. So, if it is continuous, its left limit and right limit should be equal. For all continuous function, the left hand side limit and the right hand side limit are equal, isn't it? So, limit x tends to 4 minus g of x is equal to limit x tends to 4 plus g of x. So, what is for 4 minus? 4 minus means it is less than 4. So, for this, for 4 minus, we have used this function. So, x square minus b square. For 4 plus means right side to the 4, that is greater than or equal to 4. So, bx plus 20 we can use this function. Now, we can substitute 4. So, for instead of x we can substitute 4. So, 4 square minus b square is equal to b into 4 plus 20. 4 square is 16 minus b square is equal to 4b plus 20. So, we can make a quadratic equation b square plus 4b plus 20 minus 16 is equal to 0. So, b square plus 4b plus 4 is equal to 0. We can write it as b plus 2 the whole square is equal to 0. So, b plus 2 equal to 0 and hence b is equal to minus 2. Find the points at which f is discontinuous. At which of these points f is continuous from the right, from the left or neither? Sketch the graph of f. So, here a function is given, f of x is equal to x minus 1 the whole cube if x is less than 0. X plus 1 the whole cube if x is greater than or equal to 0. We have to check its continuity. So, let us take the function again. Limit x tends to 0 minus. What is 0 minus? It is left hand limit. F of x is equal to limit x tends to 0 minus x minus 1 the whole cube. So, 0 minus means it is less than 0. So, we can use this function x minus 1 the whole cube. So, 0 minus 1 the whole cube. So, it is minus 1 the whole cube, that is equal to minus 1. Limit x tends to 0 plus, right hand limit, 0 plus f of x. So, limit x tends to 0 plus x plus 1 the whole cube. 0 plus means it is greater than 0. So, this function x plus 1 the whole cube. So, instead of 0 we can substitute 0. 0 plus 1 the whole cube. So, it is 1. Here the left hand side limit and right hand side limit is not equal. So, from these two equations 1 and 2 we have limit x tends to 0 plus f of x is not equal to limit x tends to 0 plus f of x. So, it does not exist and it is not continuous at x is equal to 0. Okay. So, we can choose few points. So, it is 0, here also minus 1, minus 2 and here 1 and 2. For 0, it is x plus 1 the whole cube because if it is equal to 0, the function is x plus 1 the whole cube, isn't it? So, for x is equal to 0, we can take this function x plus 1 the whole cube. For x is less than 0, we can take this function x minus 1 the whole cube. For x is greater than 0, we can take this function x plus 1 the whole cube. So, we can choose few random points and we can find the value. We can choose few random points for x, few random values for x and we have to find the value of f of x, that is y. Okay. Now, let us plot the points in the graph. So, 0, 1, it is a point, 1, 8, 2, 27. Similarly, here minus 2, minus 27, minus 1, minus 8. So, those are the points. Okay, Amma. So, we can plot the graph because as it is asked, we have to sketch the graph of f. Okay.